Every time we look into deep space, we are not just looking across distance, we are looking into the past. The light from distant galaxies has traveled for millions, sometimes billions, of years before reaching us. By the time it enters our telescopes, it is no longer showing us what the universe looks like today. It is showing us what the universe used to be. But for most of human history, the earliest chapters of cosmic history remained hidden. Dust blocked our view, the expansion of space stretched ancient light beyond human vision, and the first galaxies, the first stars, and the earliest moments of cosmic structure remained buried behind a veil that no ordinary telescope could penetrate. Then the James Webb Space Telescope opened its infrared eye. Suddenly, the universe did not appear older, calmer, or more predictable. It looked wrong. Webb began revealing objects that were too bright, too massive, too mature, and too organized to fit comfortably within the timeline we thought we understood. It saw distant galaxies where only faint beginnings should have existed. It exposed star formation far more violent than expected. It uncovered chemistry, structure, and cosmic machinery hidden behind dust, darkness, and time. Then came the discovery that seemed impossible. A galaxy seen only about 300 million years after the Big Bang, already far brighter and more developed than existing models predicted. It was a structure from the cosmic dawn that appeared to have grown too large, too quickly. If Webb's observations are correct, then the unsettling question is no longer what it found, but whether our entire story of how the universe evolved is missing something fundamental. The James Webb Space Telescope was never intended to be just another space observatory. It was designed to reveal what the universe had been hiding. Launched on Christmas Day in 2021, Webb became the most powerful space telescope ever constructed. A $10 billion international project equipped with ultra-sensitive infrared instruments capable of doing what visible light telescopes could never achieve. It could see through dust. It could detect light stretched into infrared wavelengths by the expansion of the universe. It could observe objects so faint and distant that their light had been traveling since the universe was still in its infancy. This capability matters because the universe has two great hiding places. The first is dust. Throughout galaxies and nebulae, enormous clouds of gas and dust block visible light, concealing newborn stars, forming planets, and hidden cosmic structures. Hubble revealed the beauty of the universe in visible light, but there were regions it simply could not fully penetrate. The second hiding place is time itself. As the universe expands, the light from ancient galaxies stretches from visible and ultraviolet wavelengths into infrared. To observe the earliest galaxies, astronomers needed a telescope built specifically for infrared astronomy. That is why Webb changed everything. It did not simply sharpen the image, it revealed an entirely different universe. Since becoming fully operational in 2022, Webb has collected an extraordinary amount of scientific data, revealing details that stretch from our own solar system to the edge of the observable universe. It has captured auroras, planetary rings, nebulae, star-forming regions, galactic collisions, gravitational lenses, and galaxies from an era when the universe had only just begun assembling itself. But the more Webb observes, the more uncomfortable the universe becomes. Scientists expected the telescope to confirm many of their best cosmological models. Instead, it continues finding exceptions. Those exceptions are beginning to look less like isolated anomalies and more like cracks in the foundation of our understanding of the cosmos. Before Webb explored the deepest reaches of the universe, it first transformed our view of objects much closer to home. Take Neptune, for example. In visible light, Neptune is famous for its rich blue color. Through Webb's infrared vision, however, it becomes almost unrecognizable. Methane in Neptune's atmosphere absorbs much of the incoming infrared sunlight, making the planet itself appear much darker. As the planet dims, the faint structures surrounding it suddenly become visible. Its rings, dusty bands, high-altitude clouds, and moons emerge with remarkable clarity, revealing the distant ice giant in a completely new way. But Neptune was only the beginning. In August 2025, Webb turned its attention toward an even more unusual visitor, 3IR Atlas, an interstellar comet that did not originate within our solar system. It arrived from another planetary system, carrying chemical material formed around a distant star. Webb discovered something remarkable. The comet contained unusually high levels of carbon dioxide and water vapor, with one of the highest carbon dioxide to water ratios ever measured in a comet. That chemical signature suggested it formed in an extremely cold region of its original planetary disk, where carbon dioxide ice could naturally freeze. This discovery matters because an interstellar comet like 3I Atlas is more than a wandering rock passing through our solar system. It is a preserved sample from another stellar system, a messenger from another corner of the galaxy. By analyzing its composition, Webb demonstrated that many of the fundamental ingredients used to build planets, comets, and potentially even life itself, water, carbon dioxide, organic chemistry, and cold planetary disks, may not be unique to our own solar system.